question, we have two cars traveling on a horizontal surface. So we'll make it up like this. And we have a car W. It has an acceleration of AW. Its initial velocity, we are told, is 0 because it's starting from rest. And then we have Z traveling across the same surface toward car W. So there is car Z. It has an acceleration Z. It also has an initial velocity of 0. So these two cars are accelerating toward each other. They're separated from each other. We're told they're separated from each other by a distance d. So which equations could be used to determine the location where the two cars will meet? Well, where they meet, two conditions are met. The position of W will equal the position of Z. And that it will happen at one instant in time. Now we're asked to determine which equations can be used and to give an explanation for it. So if we look at the first set of equations, this indeed gives us the position for car W and for car Z. So there is an equation that could describe the position for each of them. And what we know is when those two positions are equal to each other, we could set these two equations to equal to each other. And that will be the position and the time at which that occurs. Now, when we look at the second set of equations, of course, we have this for W. Well, what does this equation mean? This equation is the definition of displacement. It will tell us, for example, for car W, that if it traveled from here to here, that would give us the delta x. It would give us the change in position. But it doesn't in any way relate the positions of cars W and Z. So that means that if we are relying on this equation, it can't help us. So this choice would be out. This choice would be out. And this choice would be out, leaving us with just the first choice. And we can, in fact, since we know the initial positions, whatever they are, we could call this position 0. We could call this position 0, and we could call this, for Z, position D. If we know that distance, we can plug in those numbers. So this is known, and this is known. We know the initial velocities are 0, so that term drops out. And we know the acceleration. We're given the acceleration for x, given the accelerations of both of them. So the only unknown is the time. By setting these two equations equal to each other, we will find the time. And let's see then the explanation to confirm. We'll meet at the same time. That's true. Solving for t and placing it in the other one will eliminate all the unknown variables except for x. I do not recommend doing it that way. I recommend setting the equations equal to each other. This is really a bad explanation and a bad technique. Really, the way you should think about this is that this is a function. This is a graph. This is a graphical equation or a function, and each of them has, if we have an xt, we can plot those. And so, for example, this will look like that, this will look like that, and we're looking for the intersection. So this is really bad technique to be telling you that this is the reason, although it works. The algebra becomes really tough when you solve for one and plug it in the other. It's actually really simple. You use a graphing calculator. You put in the first equation, you put in the second equation, and you calculate the intersection. You may be able to do that algebraically when you have the numbers, but solving it all purely algebraically is a waste of time, unnecessary, and actually bad technique. But that first choice is the correct one.